In this video, we'll be taking a look at time series and the AutoRegressive integrated moving average model. Whenever you have data that is indexed or graphed in relation to time, it is referred to as a time series. In the real world, time series have a lot of application in, let's say, forecasting sales, for example. Any company that has a greater idea of what their sales will be in a better position to adjust their inventory levels, and that will end up increasing their cash reserves because they don't spend a whole bunch of money on products that'll just be sitting there for a while. And they can also anticipate customer demand, and so they can decrease the backlog of orders. Time series can be broken down into three components. So it has a trend component, it has a seasonality component, and it has a noise component. And so trend refers to the upward or downward movement through time. A common example of that would be the stock market. So the stock market goes up and down, but over the long term, it has a trend that is going up. Seasonality refers to the fluctuation of demand in relation to seasons. A common example of that would be ice cream during the summer, right? Ice cream is more popular in the summer than the winter. And lastly, we have noise, which is just random spikes in random spikes. So before we can apply any statistical model on a time series, we need to make sure it's stationary. And by stationary, I mean that the mean should not be a function of time. And so going back here, any time series that has a trend, well, its mean will change with time. Its mean will actually increase. And so a stationary time series, the mean will remain the same throughout time. Another thing is the variance will remain the same throughout time, and so variance refers to how spread out stuff is. And so you can see right here that a stationary series, the width of the curves, I guess, aren't changing, whereas here they are. And then finally, the covariance shouldn't be a function of time. And so you can see right here that the spread becomes closer as time increases, whereas here it remains the same. And the reason why we want it to be stationary is because it allows us to assume that past behavior will predict current behavior. Right? All of our historical statistical predictions or whatever else, they're based off the assumption that knowing what happened in the past gives us a better idea of what will happen in the future. Next, we will import the necessary libraries, and so we'll be using the trifecta of NumPy, Pandas, and Matplotlib. The stats models library provides a suite of tools for working with time series, so we'll be taking advantage of that. Go ahead and run that. And in this video, we'll be working with a data set of air passengers. And so essentially, for every month, it will give us the number of passengers. And I think it goes back 12 years or something like that. And if we go ahead and plot that using Matplotlib, it looks something like this. So just looking at this, we can see that it has a trend component, right? It's going up as more time elapses, and it has a seasonality component where it goes up and down, right? So you could imagine that maybe, during March break or the winter months, especially here in Canada, everybody's traveling down south. So there are two ways of determining whether a series is stationary or not. The first one being the rolling statistics method, which is basically kind of what I covered there, where you just eyeball it. And so if the rolling mean and the rolling standard deviation aren't constant with respect to time, well then the series isn't stationary. And then the other way, which might be useful, let's say if you don't really want to, trust yourself just eyeballing it, or maybe you have too many features to graph it, we can use the augmented Dickey-Fuller test. And essentially, if the p-value is low and the critical values at the 1%, 5%, and 10% confidence intervals are close to the ADF statistics, well then we can conclude that it's stationary. We'll cover that in a bit. Just for clarification, for those of you who don't know what how the rolling average differs from the regular average, essentially the rolling average will take the first 10 days and then it will compute the average, and then for the next value it will take the starting at the second day and the 11th day, and it will compute the average for that. So you can see right here, according to this table, right, so at the 10th slot right here, we have the average of the days 1 through 10, and then on the 11th, we have the average of the days 2 through 11th, and so on. All right, so we'll go ahead and ignore that. So let's go ahead and calculate the rolling mean and the rolling standard deviation for our plot. And so that's a bit hard to see. Sorry about that. I went ahead and changed it back to a white background so we could actually see. So the ideal here would be to have a rolling mean and rolling standard deviation that are parallel to the x-axis. But as you can see here, the standard deviation is increasing slightly as time progresses, as well as the rolling mean. And so just looking at this, we could conclude that it's not stationary. If we wanted to perform the AD-Fuller test, we can take a look here. And if you look at the ADF statistics, which is 0.8, it is quite different than the critical values, which are negative 3.5-ish, negative 2.88, and then negative 2.57. If we look at the p-value right here, it is much greater than the threshold, which is 0.05, and so we could conclude that this is not stationary. A quick way of rendering a plot more stationary, although it won't bring you all the way, is taking the log of the plot. So you could imagine, I know it's a bit hard to see here because it's black, but it takes the log of the number of passengers, and so the values, right, the number of passengers is closer to horizontal now. I'll go ahead and create a function that will plot the rolling mean and the rolling standard deviation, as well as doing the AD-Fuller test, or the Dickey-Fuller test. And now we'll try something else. So to actually transform our time series such that it's stationary, we could actually subtract the rolling mean. So if I go ahead and do that, you can see right here that now the rolling standard deviation and the rolling mean are a lot closer to parallel to the x-axis. And so as time progresses, it doesn't change that much. If we take a look at the Dickey-Fuller test, the ADF statistic is a lot closer to the critical values now. And if we look at the p-value, it's actually below the threshold. So the threshold is 0.05 and it's 0.02. Another way we could go about transforming our time series so that it is stationary is to use exponential decay. And if I go ahead and run this, you can see again that our rolling mean and rolling standard deviation are close to parallel with the x-axis, so they're almost constant. If we look at the ADF statistic right here, it is closer to the critical values than before the test, but it's not as good as subtracting the rolling mean. If we look at the p-value right here, it is slightly above our threshold, so it is 0.0057. Another way of transforming a time series such that it is stationary is to shift it slightly. And we can go ahead and run that. And you can see right here that our rolling mean and rolling standard deviation are almost constant. If we look at the values, our ADF statistic is close to the critical values, and the p-value is slightly above our threshold of 0.05. And so this could kind of highlight why it's important to perform the test as well as just eyeballing it, because if I had just eyeballed this, I would have thought that this were the best one, but according to this test, our subtracting the rolling mean was actually the best solution. So now what I'd like to do is I'd like to cover once we transform our time series into one that's stationary, how we can go about predicting future values. And so, like I mentioned before, we're going to look at the ARIMA model. The ARIMA model builds off a couple of things. The first one being the AR model. So AR stands for AutoRegressive, and the AutoRegressive model operates on the assumption that the past values have an effect on the current values. And the way you set it up is, so YT would be the value today. So let's say we're looking at stock prices. The value of the stock today will be expressed as a linear combination of the values of previous days. So YT minus 1 would be the stock price of yesterday multiplied by some constant. And then we have YT minus 2 multiplied again by some constant. And we refer to the number of terms, so the number of days you include in the equation is called the order of the AR model. And so if we had a AR model of order 2, then that would mean that our equation would have the two preceding days. And so we would have yesterday and the day before that. The next model I'd like to cover is the moving average model. And so I guess it's important to not necessarily get confused with the rolling average that we computed before. And so this model will be again, if we go back to our example of stock prices, so the price of a stock today can be expressed as a combination of error terms. And I tried to look up exactly how these error terms are computed, but I honestly can't tell you. But anyways, so we have the error term of today plus the error term of yesterday multiplied by some constant, and etc. And again, depending on how many error terms you have in your equation, that's referred to as the order of the MA model. And so if you have 2 terms, well then that would be order 2. You'll also see the equation written like this, where this is the mean. And so I'm assuming that the mean here would get included into the error term right here, but both are valid. The next thing I'd like to cover is the ARIMA model. And so this actually combines our autoregressive and moving average models, and it's simply just the addition of the two. And then the autoregressive interrated moving average model adds an additional component on top of that. So it actually adds differencing. And the way differencing works is it will apply a transformation. It basically subtracts the value of the preceding day. And so I have an example right here. So first order differentiating will be equal to yi, which is, let's say, the current day, and then it'll be subtract I, the day that preceded it. And then if we had a second order differentiating, then the current day would be subtracted by the preceding day, and then the preceding day would be subtracted by the day before that, and so on. And to give you guys kind of an idea of why this is useful, if we have our data with a trend right here, after one lag, which is a differentiating of order 1, it removes the trend component. And you'll typically see the ARIMA model written with 3 parameters. And so we have sorry about that. So as I was saying, basically you'll see the ARIMA model written with 3 parameters. And so P refers to the number of autoregressive terms, or the order of the AR model. So again, going back, that would be how many days we go back in our equation, or how many days we include in our equation. The D parameter is the number of differencing that we apply. And so, right, first order differentiating will subtract the current day by the preceding day. And then we have the Q parameter, which refers to the order of the moving average model. So again, that would be the number of terms to include in the equation. Come on. There we go. Okay. So on that note, we can use tests to figure out the optimal number of terms to use in our equation. And so one of these tests is the autocorrelation function, and this will give you the optimal number of MA terms, so moving average terms. And then we have the partial autocorrelation function, which will give you the optimal number of autoregressive terms. And so let's highlight that with an example. Right here, I have a graph of our partial autocorrelation function. And you can see these horizontal blue dashed lines are the significant thresholds, and then the vertical lines are the PACF values. And since only 2 values exceed our threshold, we'd want to use 2 terms in our autoregressive equation. If I had a graph of ACF, you can see here that we only have 1 value that exceeds our threshold, and so we would only include 1 term, which is yesterday, in our moving average equation. So now let's go ahead and create and fit a ARIMA model. And so we're going to be using is it AR first? I honestly don't remember. Yeah, it's AR first. So AR of order 2, differentiating of 1, and then moving average order of 2. We'll go ahead and run that. And you can see here this is the fitted values. So this is after it's been trained. And then what we can do is we can change our model back to non-stationary and plot what it would look like. And so this is what it looks like after we add in the trends and seasonal components of the original time series. And finally, if we wanted to predict values in the future, we could go ahead and use it to predict those. I'm using 264 here because it was 12 years, which is 144, and I'm going forward 10 years, so you add 120, yes. So after running that, you can see here that this is our confidence interval. And so you can imagine a company, if this were plotting demand, well then we might want to make sure that we have enough of our product to meet the top right here of the demand curve. So thank you for watching. If you have any questions, let me know in the comments, and be sure to like this video and subscribe.